So this will be the start of our lecture on Focus 3B. So I've divided this into 4 small video lectures. The entire focus is based on the entropy changes accompanying specific processes, and in each of the videos we're going to be looking specifically at different situations, so different types of changes in the system. The first one we're going to be looking at is expansion. But before we can even jump into this discussion, we need to clarify the difference between a reversible and irreversible process and how that affects the calculation of the entropy change of the universe. Right? So, using the Carnot cycle, we've already demonstrated that for a reversible process, that the change in entropy is a state function. And if you'd like to re-see that derivation, I've uploaded the document to EC Learn. You can look up the summary entropy as a state function. So, as we know, state functions are independent of path, and so calculating the change in the entropy of the system and the entropy change of the surroundings for a process is true for both reversible and irreversible paths if it is a state function, right? However, we're going to find out that the change in entropy of the universe, or delta S total, does depend on the path taken to bring about the total change in entropy of the universe, right? This seems contradictory. Delta S system and delta S surroundings can be determined to be independent of path, but somehow that the delta S total is going to be dependent upon the path. Well, it's going to be dependent upon how that change in entropy is undertaken. So when we looked at the Carnot cycle, we were dealing with a reversible process. So that means the process, for whatever was taken in place, the Carnot cycle was expansion. It means that for a reversible process, the pressure inside the system has to be equal to the pressure outside of the system at all points. So it's basically at equilibrium at every point. So it takes infinitely long to actually have a reversible process occur. So those aren't true processes that you could measure or even design an experiment in real life. But on paper, we can show that delta S total, when for a reversible process, the path will be independent. So when we add up delta S total equals the change in entropy of the system plus the entropy change of the surroundings. And we showed, at least for the Carnot cycle, that that is equal to 0, which is going to be our proof for, under those circumstances, delta S being a state function. However, we're going to find out that we already have found out, for irreversible processes, and all real-world processes are irreversible, because anytime work is done, something changes in a system, there's going to be friction, there is going to be sound waves. All of those are leaking energy that cannot be put back into the system, right? It's making eddies or currents in the air as something is expanding and pushing air out of the way. So those are processes that can't be reversed with a simple change in the direction of the process. So they are inherently irreversible, and all real-world processes are irreversible. And because when we looked at this with the Clausius inequality, we know that the delta change total, or the delta S change total, or the change in entropy of the universe, for a spontaneous process to occur, has to be greater than or equal to 0. And if you want a refresher on the derivation of that, you can look at the summary that I've uploaded to EC Learn on the Clausius inequality. But it's telling us that for any spontaneous process, the change in entropy of the universe has to be greater than 0. If the change in entropy of the universe is equal to 0, that means the process is actually at equilibrium, right? So what we're going to do here in this video lecture is we're going to compare 2 different scenarios. One in which we calculate the change in entropy total of a reversible isothermal expansion. And then we're also going to compare that to the free expansion of a perfect gas into a vacuum. So let's start first with this reversible isothermal expansion. So you could think of this as stage 1 of the Carnot cycle. So we've already derived this equation in lecture, and if you'd like to revisit that derivation for reversible isothermal expansion, that's been uploaded to EC Learn in the file Basics of Entropy. So we know that the change in entropy is going to be equal to NR ln, the ratio of volumes that the expansion took place. So, based on the first law of thermodynamics, we know that any heat that is exchanged from the system, so maybe it's lost by the system or gained by the system has to be equal and opposite in magnitude of the change in heat of the surroundings. So if we substitute the definition of entropy into the equation above, so we have our delta S, we know delta S is going to be equal to Q reversible over T. So all I've done is substitute the definition of entropy, which is the second law, into that equation. So now that we have Q reversible over temperature equals NR/Ln ratio of the volumes, multiply both sides by T, and we're ending up with the equation that for a reversible process, the change in heat is going to be equal to nRT times, that should be an L, Ln of the ratio of the volumes. Now that we know the systems and surroundings are equal and opposite in magnitude, I can substitute in the change in temperature of the surroundings, change in heat of the surroundings, and substitute it into where the change in heat of the system was. So now I have delta Q surrounding equals negative nRT, L keeps disappearing, ratio of the volumes, right? So that's our entropy change of the surroundings of an isothermal expansion. So, some things to recall. So recall that the volume of the surroundings is assumed to be constant, right? So for example, the volume of a laboratory is essentially constant from the perspective of a chemical reaction. Effectively, it's so large that even tiny changes in the volume of the laboratory are effectively negligible. So in that case, it's an approximation of a constant volume surroundings. The same thing can be said for the universe as a whole. As far as we know, the universe itself is at constant volume. Yes, the universe is constantly accelerating in its expansion. It gets a little complicated. It's beyond the course, basically beyond the scope of this course. But for us, we can effectively state that the universe is constant volume. So, under constant volume conditions, that means the change in heat must be equal to the change in internal energy. So the dQ of the surrounding equals the du of the surroundings. And since du, so the change in internal energy, is a state function, the equation for the heat of the surroundings is both true for reversible and irreversible processes. So effectively what it's doing is turning the path-dependent Q surroundings into the path-independent du of the surroundings. And so that's why my label above up here says of an isothermal expansion and not of a reversible isothermal expansion. So that's one equation we're going to keep in our back pocket. So, for a reversible isothermal expansion, we can see that the change in entropy total, so the change in entropy of system plus surroundings, is going to be equal to 0. And we've actually already shown this with the Carnot cycle. So here we have nRT ln, that should be an L, I don't know why the L keeps disappearing, is our ln of our ratios of volume. So this is indicating the system, and we know the surroundings is going to be opposite but equal in magnitude of the delta S of the system. When we add that all together, excuse me, that the change in entropy total must be equal to 0. So, this result shouldn't surprise us because we've already seen this with the Carnot cycle. Basically, it's the sum of the two isotherms seen from Carnot stage 1 added to Carnot cycle stage 3. They cancel and lead us to the conclusion that the change in entropy of the system is a state function. This also proved thermodynamically that the delta S total, the change in the entropy of the universe, of a reversible process is a state function. So for a reversible process, delta S total is a state function. So if we graph this, so this is the graphical interpretation of delta S total of a reversible isothermal expansion. So we can see the logarithmic dependence on the change in entropy of the ratio of TF to TI, and that's what we see here. We go up here. There's a logarithmic relationship between delta S. These are constants, but there's the ratio. It's dependent. It's a logarithmic relationship between delta S and the ratio, and that's what we see in this graph, right? So if we plot delta S over NR, all we're doing is rearranging the equation versus the ratio of volume final over volume initial. We see the logarithmic change in entropy of the system, and so I took this from figure Atkins figure 3b1. So if we plot the same variables from the perspective of the surroundings, though, so this is not on the graph, but we can imagine this, you would see a mirror image of the curve. So it would basically start up here, and you'd see a mirror image of the curve. If you added those two curves together, well, they would cancel out, and it's exactly what we're seeing in this equation up here. So both using the equation and using graphically, we can see that for a reversible isothermal expansion, the change in entropy is going to be equal to 0. So that was our first example. We said our second example is then going to be comparing it to a non-reversible process. So we're going to be looking at the entropy change for an isothermal free expansion. So let's remind ourselves what a free expansion is. So we're going to recall that a free expansion is essentially a system expanding into a vacuum. There's literally nothing to perform work on the gas to reverse that process as it moves into the vacuum. So therefore, there is no work being done by the gas. The gas does not have to push anything out of its way. It just freely expands into this new volume. Hence the name free expansion. So under those conditions, work is going to be equal to 0. Free expansions are inherently irreversible, right? Because we said there's no way, there's nothing to push back against to force the change in volume to return back to its original state. We'll also put this under isothermal conditions. So in case of isothermal, that means the change in Q of the system has to be equal to 0. And according to the first law, that means if there's any change in the heat of the system, well, something had to make up for that. And so that means the heat exchange with with the surroundings will be dumped into the system so that total, they'll be equal to 0. So there is a heat exchange with the surroundings, but it keeps the total change of Q equal to 0. So what we can do then is substitute this equation back into our definition of entropy. So the change in entropy of the surroundings equals the change in Q of the surroundings over the temperature of the surroundings. If the change in the Q of the surroundings is equal to 0, well then the total entropy change is going to be equal to 0 as well. So let's look at this. There is no change in the heat of the system, and the gas will be expanding into a larger vacuous volume. Therefore, based on statistical entropy, right, the entropy of the system is increasing because of the greater access to translational microstates. So let's put that into context. So as this system expands into a vacuum, right, no work is being done, and there's no exchange of heat. So usually you would say, well, if there's no exchange of heat, just like we see dq surroundings, you would say, oh, the change in entropy of the system must also be equal to 0. If that were the case, that means that gas actually would not freely expand into a vacuum. It would just stay where it is, which we know is not true. What's driving that? So if it's not the change in heat, we also have another definition of entropy in terms of statistical entropy. So this is what Boltzmann derived, where entropy equals the Boltzmann constant times the natural log of the microstates. So as you increase the volume, there are more ways to arrange that system, right? There is now more microstates that the system can be arranged into, and if there's more microstates, that means the entropy had to have increased, even though there's not an exchange of heat. So in that case, the change in the entropy of the system is going to be a positive number, and that system is still going to be equal to nR ln, the ratio of our volumes. So if we substitute back in our equations for d of the delta S of the surroundings and delta S of the system back into our equation for delta S total, we find out that d surroundings is 0, so therefore the change in entropy total is actually equal to nR ln of the ratio, and therefore delta S total does not equal to 0. Therefore, under these conditions, the delta S total is not a state function. So depending on what path we took, we could get a delta S equal to 0 or a delta S not equal to 0. So that means that the delta S total is going to be path independent.